Hi, Paul with Diode Dynamics, and today we're talking LED headlight bulbs. So you've got your bulbs, they're lighting up, they look bright, and that's it, right? Well, maybe not. If they're running too hot, they're not gonna last very long, or they're gonna lose their brightness over time, something we call lumen maintenance. For that reason, it's really important that they're well designed and they're not running too hot. Let's start by taking a look at some common styles on the market and see how they perform. For our test here, we have a fixed scale set, so 85C is white hot and 35 is the dark blue. And for the bulbs we have, we just picked some standard designs. So two of them don't have fans. The first is this one here, which is what we would call a passive heat sink. And we've let these run for an hour to get to a steady temperature. You can see this one is just saturated with heat throughout. No major hot spots except for those chips, but that's about what we'd expect with that thermal energy just going through the metal on this one. Pretty hot overall though, not too bad, running at a decent power level. This one is one of the bulbs that has braids on it, or fins, and you can see that on the camera here, how the entire top of the bulb is just white hot, super scorching. Where the chips are, it's 120C, and then the fins are doing a decent job at getting some heat out. You can see how it's cooler down there, meaning the thermal energy is coming from the top all the way out to the fins. But this one's maybe a little overpowered. The whole bulb is very hot. The entire thing, even the base, is white hot. So decent, but maybe a little bit too much power. This is a traditional bulb using a fan on it, and you can start to see the effect of a fan on the bulb. The bottom here is a blue color, or green, and so the entire base is cool to the touch where that fan is. So the idea is we're gonna pull the heat from the chips all the way down to the base of the bulb. And this is doing a decent job at it. You can see 120 at the chips, but we don't have saturated heat all around those chips, so definitely doing a decent job. This one is super hot. Actually, it's literally burning holes in our tablecloth here. You can see how this one also has a fan on it, so it's pulling this down, but the entire top is just scorching hot. So really, really hot up top. And the bottom, no dark blue. So it's pulling the heat away, but it's also running at a very, very high temperature, and we don't have a real effective cooling system because it's not getting very cold at any point. Finally, we have the SL1 bulb, which we designed. Of course, we might be a little biased, but this really doesn't lie. You can see the entire bulb is blue on the camera. It's cool to the touch, even the casting I can touch here. And that's because it's a very effective cooling system with our fan to keep everything cool except just the LED chips there. So running at less than 100C on the chips, that's gonna keep full output for a very long time with a nice cooling performance. All right, so as you can see, there's a lot of differences in the output and the performance of how the heat comes out of those bulbs. And again, this is important because if we're running at a high temperature, the LEDs are gonna lose light over time. As you could expect, this is a big focus for OEMs who know that their LED headlights are going to be on the road for 10, 15, 20 years. This is something called lumen maintenance. We have to make sure that LED chips are running at the expected temperature at a nice cool level so that they're going to last over time and not lose output. If they're running too hot, they're going to lose output in just a couple months. So why is this happening? When we have our LED bulb here, why and what goes into it to achieve this certain thermal performance? We're going to take a look at every component of this, starting with the LED chips. Taking a look at the LED chips, there's one major distinction between the LED chips used. On the right side here, we have a more traditional LED chip, and that has two connections or pads on it to the circuit board. Those have to be used for positive and negative to make our electrical connection. On better LEDs, we're going to have three connections. Positive, negative, but then one extra one specifically that's isolated to get the thermal energy out. We call this a thermal slug or an isolated pad. That allows us to bond that LED chip to the circuit board specifically to get the thermal energy out, meaning we can get better thermal performance. Now from there, the next important thing is our circuit boards. So the majority of circuit boards out there are going to be fiberglass core, FR4. This is most commonly used on drivers, big motherboards, computer circuits, everything, because it's very cheap and it works great when you don't need to get rid of the energy. Here we have one of our driver PCBs. They're normally green in color. Now, even with that fiberglass core, we can still do a pretty good job, like this Philips LED bulb PCB here. It's from a Philips fog light bulb. If we extend the copper throughout, so we actually have a layer of copper that's the electrical traces on the top, we can put a plane on it or a big copper area, and that's going to help get rid of the heat even though it's a fiberglass core inside. So it's a neat, interesting way to still keep your costs really low, but do better with the thermal performance. Next, the most common type of board we will see and use is an aluminum core. So if we look at the side of this, you can see throughout it's an aluminum material. And so the whole PCB is going to start acting as the heatsink for us to really pull the heat out of the chips. These are our charger RGBW boards. We use these to run the high power LEDs, but you'll find aluminum in street lights, basically anything where high power LEDs are used. A lot of light bars use those. Very common and not too expensive. Now the best performance we can use is a copper core PCB. And here we have an SL1 board here. We actually have another LED headlight bulb that has the copper core inside though. So any really high performing LED bulbs are going to use copper core. But even if it's copper, there's one important note. The best copper core PCBs are going to actually connect the LEDs themselves directly to the copper core. The most common way to make the connection is like this one, where we connect the LEDs to just the top layer for electrical purposes. But because we have the isolated pad on the better LEDs, we can actually design the LED board to bond the chip directly to the entire core of the material. This is an expensive process, but by doing this, everything is directly connected. We call this a direct solder point or a direct connection to the core, and it's the best way to pull the heat out. Now, after the circuit board, the next step is getting it from the circuit board to our heatsink. So between the two, there's an air gap. Any little areas of material, just this rough surfaces, that's going to be resistance. Air is an insulator. So we need to put something between that. Now, the cheapest way to do it is with this bulb here. We have a thermal paste. So it's just a little paste material that we can spread down and then put our circuit board on top of it. Now, the problem with the thermal paste is, as you can see, we only have a little strip of material on there. So it's not covering the entire area. There's a lot of air gaps left and a lot of resistance. This is very common though, just because it's so cheap, really easy to do, just squirt a little bit down and your board can go down. It's just not going to be as effective, and it's also pretty messy. We then have thermal interface materials, which is what we call TIM materials. So the most common or biggest supplier is Laird. There's also Bergquist out there, but this is actually a phase change material. We have some cut out here for the SL1 bulb, and as you can see, they're going to completely cover the circuit board in all areas. And what's interesting here is it's not tape. You might think it's an adhesive, but it's really not. It's kind of a interesting material. It's a little sticky to stick down, but it's not, we can kind of pull away at it, and it's kind of almost a putty. And what it'll do is, as it heats up, it'll actually flow into all the little crevices on the circuit board and the casting, filling in those areas, and that's why we call it thermal phase change material, TPCM. Now, there are some silicone-based films as well that are not going to fill in. They're going to be blue or greenish in color. Pretty effective, but just not quite. Now, one other thing you might have seen is graphite material. Graphite is, of course, very conductive, and it looks really cool. As you can see, a whole sheet of it here. But the problem with this is that it's not going to fill in every single gap. So unless your surfaces are super, super polished smooth, it's not the most effective solution. It's also a little bit messy, and it is electrically conductive. So if you need to isolate things, it's not going to work. So we have the energy now to the outside of our circuit board with that interface material, and it's all about getting it to our heatsink or our casting. So here we've got a couple different heat sinks. These are most commonly just going to be aluminum, and as you can see, this plays the biggest role in the look and the styling of the bulb, but they're functional as well. And we say functional because these are responsible for getting the heat out and to the air. And if you look at the design of these heat sinks, a lot of them just aren't very well designed. It's a lot of science that goes into how the air interacts with the metal, and if these heat sinks are too close together, or they're not allowing enough air to flow through, it's just not going to get rid of the heat very well. And a lot of these are just styling only. You can see with the Diode Dynamics SL1 casting, we put these two pieces together. This is a very deliberate design and modeling here where we have the fan that sits on the bottom and actually blows air through these fins that are spaced just enough. And we did that with something called CFD, Computational Fluid Dynamics Modeling, to actually see the airflow and how it goes through to expel the maximum amount of energy possible. That's really important if you want to achieve good cooling, so it's where a lot of bulbs really fall apart. So that's the casting of the bulb. Finally, some bulbs are going to have fans on them, which is what we call active cooling. So the big problem with fans is that there's a huge difference in low quality and high quality fans. Good fans can cost 10 to 15 times as much as a really cheap fan, even though they look really similar. And just like any moving part in a vehicle or anywhere, it has to be made with precision, and that's why we have so much of a cost difference. Everything needs to be really nice and tight to keep it running. So we either have bracket type with no frame around it, or a frame type, which is more common. Whether it's a tiny little 20mm fan, or a 30 or even bigger like a 50mm diameter, they're all going to serve the purpose of getting more air to go over our heat sink fins and pull more of that thermal energy away. So as you can see, there's all kinds of different factors and variables when it comes to the LED bulb's thermal performance. But one thing is for sure, it's always better to have a cool performing bulb. You want to keep those LED chips nice and cool so that they'll last really well over time with a high level of output. A lot of bulbs on the market, they're going for the highest output they can, so they're really overpowering those chips, running them too hot, and they're just not going to last very long. Maybe 6 months, maybe a year, but they are going to reduce output and maybe go out prematurely compared to well-designed bulbs. If you wanted more information, please feel free to check us out at diodedynamics.com. Thanks for watching.